In this episode, we're going to be talking about statistical sampling. So what is statistical sampling? In fact, what is statistics versus probability? Probability is, well, let's say that we know exactly how many marbles of each type are in a pail, and we grab a handful out. What's the probability of us finding, for example, 2 white marbles, 3 green marbles, and a gray marble in our hand? So we already know what's in the pail. We just want to know the probability of selecting certain numbers or types as we grab a handful. Statistics, on the other hand, is given the information, I've got these marbles in my hand, what does that tell me about what was actually in the pail originally? So in other words, I don't have full knowledge of what was in what we call population. I only have the knowledge of what's in my hand, and I'm inferring or guessing what's out there in the population. So let's consider a random process that's got a random variable x. In probability, the type of distribution and the mean and the standard deviation would be known, and we would use this information to compute the probability of various outcomes of x, right? So this sort of example. In statistics, the type of the distribution, the mean, and the standard deviation are all unknown. So we have to guess at what those are. We want to sample the output x, right? Here's sampling, and then estimate what the mean and the standard deviation are from those sampled data. We use this information to try and determine the type of distribution. That's called parametric estimation. So here's a few concepts about data. When we say population, we don't just mean people. So we could say it's all students in Oakland University might be the population, but it could also be all the marbles in a pail or all the potential voters in the country. That's the whole population. A sample is just some kind of subset or subgroup of that population. So it could be the students in a room, or it could be the voters in a county. A variable is a property or attribute of each unit. So, for example, you might say that all the people have ages, all the people have heights. That would be like a column field within a table. And then for an observation, we'd say the variables, or those would be the values of all the variables for an individual row. So it would be, for example, all the information related to a person, their height, weight, age, and so forth. So properties of measurements, I think probably the easiest way to see some of these properties are, well, let's look, for example, first at the idea of precision. Precision means you're spot on. It's a spread of the estimator of a parameter. You can see that the precision here is not very good. Precision here is really quite good. Accuracy, well, how close is that estimator to a true value? So this is quite accurate. This is accurate, but it's not very precise. This is precise, but you're going right off target, so it's not very accurate. Bias is systematic deviation of an estimate from its true value. So we'll see some of that later on. Of course, the idea of a statistic itself, that's a numerical function of sample used to estimate a population parameter, and the parameter is a numerical characteristic of the population. So we might say the proportion of people that support deer culls, for example. We always want to know, are we taking a good sample? Is whatever we're sampling a representative sample? Are there any pre-existing biases, any unavoidable errors? The classic, of course, is Dewey versus Truman, that one presidential election where Dewey was predicted to be the next president, but it turned out that they were sampling people who had telephones at that time, and that was not a very representative sample, and so that's why they misjudged that election so badly. Even today, we often have misjudgments. We think we've got a representative sample, but it actually isn't. So what's it all about? In many random processes, the randomness in the outcome is due to an accumulation of a number of different factors. Usually, these factors, they can make, for example, a part be a little bit bigger, a little bit smaller. You could have things like gear backlash for this industrial robot where we've only got an accuracy of 1/2 inch. And all of these different sources, the contributing factors of the inaccuracy, can take things randomly either bigger or smaller, and they add up in such a way that in the end we have a distribution that is really a normal curve, right? Because after a while, well, most things will cluster around the center, but we'll have the probability, a small probability of going out towards the tail. So to understand this, we often look towards the central limit theorem. And what this theorem says is that as we take samples from any population, the sample mean, right, as we take a bunch of those, so we're going to take a sample mean of, n samples. And let's say we take a bunch of these sample means. Those sample means are going to cluster in a normal distribution, so the underlying population we may be selecting from could be normal, could be whatever we want, but the means are going to also have a normal distribution. But that normal distribution is going to be much tighter, cluster around the mean in a tighter fashion than the original population. Why? Because as we take each sample, it's bound to, the larger the sample that we take, the more likely that that sample will have a mean, x bar, that will cluster closely around the true mean of the sample. So let's give you a visualization so you can understand that a little bit better. Okay, so here we have typical normal distribution, and we're going to take a sample of, we're going to take a sample of 5 different values from this normal distribution. Now you're going to expect that as I take each of those 5 samples, they'll probably cluster more around this central area because the probability is higher there that I would get a sample from there. Let's try it. Okay, boom. You can see I took 5 values. They did sort of cluster more towards the center, right? And the mean is right here, just off just a little bit from the true mean. Let's try again. Okay, another one. Oh, okay. And one more. Oh boy, they're all plopping right on top of each other. See, I only got one that was really an outlier. Let's try again. Hopefully I'll get something different. Oh, I did. In fact, let's try doing 5. Oh, and 5 more. 5 more. In fact, let's do 1,000. Look at this. We took 1,000 samples of 5, and what we got was not exactly this normal distribution. In fact, those samples had means that clustered more tightly. Here you see, right here. Let's see what happens if I clear this out and I take a little bit larger samples. We're going to take, let's take, instead of 5, let's take 16. Okay, we're going to take 1,000. Well, first we'll animate it. It's going to take, there we go, 16 samples, and there's my mean. Now, let's do it 5 times. Let's do it 1,000 times. There we go. Look at this. This actually has a tighter distribution even than before when I can't actually run it at the same time, but now watch. I'm going to take it back down to 5, and you'll see this is a little bit broader when I do that. Okay, oops. No, we don't want to go 2, we want to go 5. Okay, so we're going to clear it, and we're going to do 1,000 again. See, it's broader. Now let's try doing, let's see, 25. That's as good as we can get. We're going to do 1,000. Look, now it's even tighter distribution. In fact, whatever that standard deviation of this upper normal curve is, this one has got a standard deviation that's smaller, and it's smaller by this amount, 1 over the square root of n. So this is whatever this standard deviation is divided by square root of n, which is 25, square root of 25, which is 5. Now I'm going to show you something kind of really cool. Let's do a custom. Okay, I'm going to do just a totally bizarre distribution. Be like this, right? So I've just made a completely bizarre distribution. And let's take a sample of that. Okay, so we're going to take, this time we're going to take, well, let's leave it at 25. We're going to take 25. So look, there it goes, 25. Okay, there's our mean. Now we're going to do this 8,000 times. Look at that. In fact, let's do this 10,000 times. Look at this. Totally bizarre distribution. But when I take the sample means, the distribution of all those sample means for n is equal to 25, look at that. We get a normal curve. It's amazing. So that brings us to, I think, a very nice website here by Charles Annis. He talks a little bit about the central limit theorem, and I like the way he phrases this. That is, he says the central limit theorem is responsible for this remarkable result. And that's what we just saw. The distribution of an average tends to be normal even when the distribution from which the average is computed is decidedly non-normal. So let's go down to the bottom of the page where he has a wonderful little animation. Watch this. He's changing the sample size and then taking the distribution of the means. Notice that as the sample size gets larger and larger, the means, or the sample means, cluster more tightly around whatever that true mean actually is. Now let's work a problem that can give us a little bit better understanding of these sorts of ideas. We're told that if all possible samples of size 16, in other words, n is equal to 16, are drawn from a normal population with mean is equal to 50, so mean is equal to 50, n is equal to 16, and the standard deviation is equal to 5.5. What's the probability that a sample mean, x bar, will fall within this interval right here? So this is actually much more straightforward than you might think. What we do is we look for the probability that mu x minus 1.9 sigma x is less than x bar is less than mu x minus 0.4 sigma x bar actually. So that's actually, remember that these are just essentially z values. We're actually looking for the probability that 1.9 or minus 1.9 is less than z is less than minus 0.4. So if you go and look on the tables, from minus 1.9 you'll see an area of 0.3446, and for minus 0.4 you'll see an area of 0.0287, and all of that is equal to 0.3159. So here's our true population. Here's our population of sample means, right like that. So now I might ask you to continue. Okay, so then tell me exactly what that interval is, not normalized, but actually on the real scale. To do this, we want to remember that this underlying population is characterized by a mean and by a standard deviation. This population of the sample means is also got a mean that is hypothesized to be at the true mean, and it has a standard deviation x bar that is actually this standard deviation divided by the square root of n. So what that means is when we calculate these z values, right, we have to plug into our usual formula. Z is equal to x minus mu over sigma, but in this case it's sigma x bar. It's this distribution is the one that we're dealing with. So that's the same as x minus mu over sigma divided by the square root of n. So, okay, so now we plug our z's in. We're going to plug in z is equal to minus 1.9 is equal to x minus, what was our mu? It is 50 all over, let's see, 5.5 divided by the square root of n, so it's divided by 4, right? Square root of 16 is 4. And when we work that all out, x is equal to 48.6. Okay, so that's minus 1.9. Now let's figure out what's on this side, which is minus 1.4. So we'll just do this the fast and dirty way. We'll just erase the 1.9 and we'll put instead in 1.4, and we'll solve again for, that was x1 the last one, and now we'll solve for x2, which is the other side, and that becomes 49.45. And so this value, these values right here, and that's the area that we're looking at, and this x1 in reality is going to be minus 48.6, and this x2 is going to be 49.45. So remember, when we're talking about the sample means, we are talking about something that's divided by with the standard deviation divided by the square root of n. Now note, we know a little bit more from the central limit theorem, and that is the only thing that we would know about each of those random variables is their mean, right, and their variance. So the random variables may be n samples of the same random variable from a random process, or random variables from n different random processes. So note that random variables can be all discrete, all continuous, or a mixture of both discrete and continuous. So the approximation, z of however many n is in your sample, approaches the normal curve. That approximation gets better the more samples n that you take. it becomes exact as n goes to infinity. So in general, a good rule of thumb is that the central limit theorem can be used if we've got more than 30 samples. We can get accurate results using the central limit theorem for some distributions if we've got a lower number. For example, if it's n is equal to 12 will work well for uniform distributions. There's a few distributions that actually require an n greater than 50 to get accurate results. So a little more about the central limit theorem. It's useful for any random process where the output is due to an accumulation of several different factors. So if we're making the diameter of a finished part, the randomness of that diameter could be due to many different factors, including the machining, the final machining operation, or individual prior machining operations, or fixturing variations. So the fact, or if we model this diameter using a normal curve, it's a good choice for that distribution. Now, if we're doing statistical sampling, we say we have a random process with a random variable x, and we randomly sample n outputs from that process, and we're going to label their values x1 and x2 and so forth all the way up to n. The mean is calculated in the usual way. The sample standard deviation is given by S, which is we take each one of those values and subtract it from the sample mean, square it, add them all together, and then we divide by n minus 1. This is a little bit different than the true mean, right? That sample mean is not necessarily the true mean. And also the standard deviation, which is maybe, in fact may well be, different than the sample standard deviation. So an alternative formula for calculating the sample standard deviation is just this rascal right here. It's large, it's complex, but it works. So statistical sampling, look at this. If we have distribution parameters from an actual population, we're going to have a mean and a standard deviation. If it's from a sample population, we're talking about the mean of our sampling distribution and also the sample standard deviation. As our number of samples gets larger, these estimates are just going to get better.
로드러너 길을 건너네 아무도 로드러너 막지 못하네 로드러너 하루 종일 달리네 하루 종일 삐삐 때문에 쉬지 않고 달리네 로드러너 누구도 못 막아 로드러너 막으면 혼나